Hello everyone. So we begin looking at test case design algorithms in this module. What I would be starting is to model software artifacts as graphs, which will be one of the four structures that we would consider. If you remember, we said we would consider graphs, we would consider logical expressions, we would consider sets that model inputs to software, and finally we would consider the underlying grammar from which a software programming language is written, right? So we begin with looking at test case algorithms that deal with graphs. So while we look at test case algorithms that deal with graphs, I would like to recap some basic terminologies related to graphs as we would be doing in this course in testing. Graphs and graph theory are vast areas. I will not be able to do justice to be able to cover even the basic minimum concepts that we deal with in graphs. So we will restrict ourselves to just looking at terminologies that we need as far as test case design algorithms are concerned in this course. So graph theory is a very old subject. It is believed that study of graphs was initiated by Euler in the year 1736 when they were trying to look at this city called Königsberg in Russia, and then they were trying to model a problem of crossing the bridges in the city in a particular way. So they considered modeling this problem as a graph, and graph theory is supposed to have originated with Euler's theorem, which is considered an old theorem. So you can imagine how old graphs is. Today, graphs enjoy applications not only in computer science but in several different areas, all sciences, physics, chemistry, biology, and in fact it finds extensive applications in sociology, where people look at social networks and other entities as very large graph models, right? So what do we do with graphs? We will consider graphs as models of software artifacts and see how to use graphs to design test cases as we want them. So if we begin by introducing what a graph is, I assume that you've not seen it before, so I'll introduce you from the very basic concepts. If you've seen it before, feel free to sort of skim through these parts because they'll talk about the basic terminologies related to graph. So how does a graph look like? It looks like this. So this is what is called an undirected graph, which is simple in the sense that it doesn't have any self loops. And here is what is called a directed graph, where the edges have directions. So graphs have two parts to it. There are nodes or vertices. Sometimes I'll use these terms synonymously, interchangeably. Some people also call it as points, and different books might call them differently. So that is typically a set that is marked using circles like this. Each circle is given a number. So there are 5 vertices or nodes in this graph, which are labeled as U, V, W, X, and Y. Similarly, there are 3 nodes or vertices in this graph labeled as P, Q, and R. And graphs also have what are called edges. Edges are also called arcs or lines in certain other books. So what is an edge? Edge is basically a pair of 2 nodes or 2 vertices. So this pair of nodes or vertices can be ordered or unordered. So if the pair is unordered, that is, I don't really worry about whether I'm looking at the pair U, V or V, U, right? Then I say that the graph is an undirected graph. And if the pair that I look at is ordered, like if I look at this figure of a directed graph on the right, I am looking at an ordered pair P, R. So there is an edge in this direction from P to R, and in this graph there is no edge in the reverse direction, right? So such graphs are what are called directed graphs. Of course, it is to be noted that an edge can take a vertex to itself. There is no requirement that U should be different from V. So if you look at this directed graph, the pair R, R constitutes this edge, which is the self loop around the vertex R. So when I look at a pair R, R in a directed or an undirected graph, because it's a reflexive pair, I really don't worry about whether the pair is ordered or unordered, right? It doesn't matter. Otherwise, for each other pair of distinct vertices, whether the pair is ordered or unordered defines the kind of graphs that we look at. Graphs could be directed as it is here or undirected as it is here. So graphs can be finite or infinite. So a finite graph typically has a finite number of vertices. An infinite graph has an infinite number of vertices. because our use of graphs in this course is to be able to use them as artifacts that model various pieces of software. We will not really consider infinite graphs. We don't really have the need to model any kind of software artifact as an infinite graph. So we will look at finite graphs throughout this course, right? A few other terminologies in this graph. What is the degree of a vertex? The degree of a vertex gives you the number of edges that are connected to the vertex. Another term for connected that people use in graph theory is to say that an edge is incident on the vertex. So if we go back to the graph examples that we have in the previous slide, if you take this vertex u in this undirected graph, three edges are connected to this vertex u, right? One coming from w, one connecting it to x, and one connecting it to v, right? So all these three edges are supposed to be connected to u or incident on u, and so the degree of the vertex u is 3. So similarly, degree of the vertex y is just 1 because there's only one edge that is incident on y. So if you go to this directed graph, the degree of the vertex r would be 3. So when we count the degree of a vertex for an undirected graph, we count the in degree of the vertex. In degree is the number of edges that come into a particular vertex. So here there are three edges that come into R. One from P, one from Q, and one from R. So we say R has in degree 3. Right? Similarly, we also talk about an out degree of a vertex in a directed graph. So if you look at the vertex P, P has in degree 0 because there is no edge that is coming into P, but P has out degree 2 because two edges go out of P. If you look at the vertex Q, Q has in degree 1 because this edge from P to Q comes into Q, and Q has out degree 1 because this edge from Q to R goes out of Q. Right? So moving on, the graphs that we will look at will have several other things apart from just vertices and edges. So one at a time, we look at what are the add-ons or the additional features or annotations that we will consider to be a part of the graphs that we look at. Right? So graphs could have special designated vertices called initial vertex and final vertex. So what I have done here is I have taken the same graph that you saw 2 slides ago and marked the vertex u as an initial vertex. U has an edge that is incoming, a line that is incoming into u, but it doesn't really have any vertex on the other side. So such a vertex is what is called an initial vertex or an initial node. There could also be what are called final vertices. Final vertices are believed to be vertices that capture the end of some kind of computation in the models that we will look at. When we look at graph models corresponding to code and corresponding to design elements, it will become clear what is the purpose of final vertex. But for now, you can understand it to be a final vertex is one in which computation is supposed to end in some way or the other. And in our pictures that we will look at, final vertices will be marked by this concentric circle. So if you see in this directed graph, P is an initial vertex and R is a final vertex. In this undirected graph, U is an initial vertex and W is a final vertex. So typically we believe that most of the software artifacts that we will consider, like code mainly or design, is always supposed to be deterministic in the sense that its behavior is definite and there is no non-determinism in its behavior. So to be able to capture graph as a model of a software that is meant to be deterministic, we will always say that the graph will typically always have only one initial state, right? If there were more than one initial states, then it will be a bit confusing as far as determinism is concerned, right? Because if there are more than one initial states, let's say there are 3 initial states, where would you consider the computation is beginning from? You could interpret it as it is beginning from any one of the initial states, but then right there, the software is non-deterministic, right? And we really don't typically look at non-deterministic software. Non-deterministic implementations of software don't exist. We always look at deterministic implementations of software, and hence we will consider our graph models to always have only one initial state. But software, as it's executing, could take one of the several different execution paths that it goes through, and based on the path that it takes, it could end in one of the many different states that it is in. So typically, graph models that represent software artifacts will have more than one final state. In this example that I have shown in this slide, it so happens that both these graphs have exactly one final state, but that need not be the case in general, right? So what is the summary of this slide? So certain vertices in graphs which occur as models of software artifacts could be marked as special initial vertices from where computation is supposed to begin. We will identify them by this incoming line, right, which is not connected to any vertex on the other end. And some vertices are marked as special final vertices, which are marked by these double circles, as you can see in these two figures, and they are supposed to represent vertices in which computations end. Another point to note is that there could be graphs in which both initial vertex and one of the initial final vertices is also an initial vertex. It's not nothing that is specified which says that the set of initial vertices and final vertices should be disjoint. There is no requirement like that, right? So how are we going to use them as graphs, right? Why do we need to look at graphs as far as software testing is concerned? Graphs, I believe, are the next to logical predicates maybe, are the very popular structure used in testing, right? Several testing and static program analysis tools use graph models of software artifacts. So where do these graphs come from? They could come from several different sources in software artifacts. They could represent control flow graph of a particular program. Don't worry if you don't know these terms. We'll introduce each of these terms as we move on in the course. They could represent what is called a data flow graph corresponding to a piece of code. They could represent what is called the call graph corresponding to a piece of code. They could represent a software design element, which is modeled, let's say, as a UML finite state machine or a UML state chart. They could represent a requirement, which is given as a use case diagram or an activity diagram in the UML notation. All these are basically graph models that represent several different artifacts. Now you might ask a question, the kind of graphs that I defined to you just a few minutes ago just had vertices, edges, and maybe some vertices marked as initial vertices and some vertices marked as final vertices, right? Obviously, the kind of graphs that I'm talking about here through these different software artifacts are not going to be as simple as that. They will typically have a lot of extra annotations or labels as parameters, right? They could be labels associated with vertices, they could be labels associated with edges, and so on and so forth. So as and when needed, we will look at a corresponding kind of graph, but no matter what the kind of graphs they are, they will always have this underlying structure. They'll have vertices, some vertices marked as initial vertices, some vertices marked as final vertices, and a set of edges. The edges could be directed or undirected. They will always have the structure and a whole set of other things, right? And how are we going to use? Our goal is to be able to design test cases that will cover this graph in some way or the other. Covering in the sense of coverage criteria that I defined to you in one of my earlier lectures, right? So here is an example of how a typical graph occurs as a model of a software artifact. Another thing that I would like to reiterate at this point in my course is that when we look at examples like this, I will never show you a complete piece of code that is fully implemented, right? I will always show you a small fragment of code. Like if you see in this example, I have just shown a small fragment of code. This doesn't mean that this is the entire program, right? It can never be a full complete program, and it doesn't make sense as a full complete program because you don't know what its inputs are, what its outputs are, where are the outputs being produced. It's clearly not an implementation ready code, right? We'll always look at fragments of code that is useful for us to understand a particular algorithm or a methodology for test case design, right? We will never, and we will of course see examples where we will see full pieces of code. But as I go through my lecture, we will see a lot of code fragments, right? So don't confuse them with the code that is ready for implementation. It will not be the case. So here is a piece of code fragment which talks about an if statement. So there is an if statement which says that if x is less than y, which means if this predicate turns out to be true, then you go ahead and execute these two statements. What are these two statements? One says y, assign 0 to y, and the other says make x is equal to x plus 1. And if this predicate turns out to be false, then you say x is y plus 1, and no matter what you do, when you come out, you make z as x plus 1, right? So here is a graph model corresponding to this particular code fragment. How does this graph model look like, right? So corresponding to this first if statement, there is an initial node in the graph, which is marked here, right? This if statement basically tests for truth or falsity of the predicate x less than y. So if x is less than y, this code takes this branch. If x is not less than y, which means x is greater than or equal to y, then this code takes this branch. Suppose x is less than or equal to y, then these two statements have to be executed, right? So when it takes this branch, I model one collapsed control flow node, which basically represents the execution of two statements in the order in which they occur. The two statements are as they come in the code. Assign 0 to y, assign x plus 1 to x, right? Suppose x less than y was false, then the code takes the else branch and it comes here and it executes the statement x is equal to y plus 1. So it doesn't matter whether it takes the then branch or next branch. As per this example, when it comes out of the if loop, it executes the statement. So no matter whether it goes here or it goes here, it always comes back and executes this statement. So this is how we model control flow graph corresponding to a particular program statement. So later I'll show you for all other constructs, for loops and other things, how those control flow graphs look like. Here is another small example. Let's say suppose you take the same if statement, but it didn't have the else clause, right? So there is nothing that is specified in the code about what to do when this condition, when this predicate x less than y is false. It doesn't matter, people can write code like that. In that case, what you do is if x is less than y, from here, this node which represents this if statement, you do these two statements at this node, which is assign 0 to y and assign x plus 1 to x. And if this condition x less than y is false, then you come directly and execute the statement z is equal to x plus 1. So if you see this kind of graph, the graph that we saw in this slide or the graph that we saw in this slide, they have vertices as we saw. Then they have a designated initial vertex. I have not marked any vertex as final vertex because I don't know whether the computation of this code fragment ends here as a part of the larger code or not. And in addition to that, if you see, both vertices and edges have labels associated with them. These vertices, this vertex is labeled with two statements from the program. This vertex is labeled with one statement from the program. These two edges are labeled with what are called guards or predicates that tell when this edge can be taken, right? So like this, typically all other models of graphs that we will look at, which is from this list, we will always look at some kind of extra annotations or labels that come with these kind of structures, right? So another important concept that we need related to graphs as it's used in testing is a notion of a path in the graph. Think of a path as the graph as sitting at some vertex or a node and just using the edges to walk through the graph, right? So what is a path? A path is a sequence of vertices, just a finite sequence of vertices. I told you we'll consider finite graphs. Finite graphs doesn't mean that they give rise to finite paths, because a graph could have a cycle wherein you can take it again. Cycle is a path that begins and ends at the same vertex, and you could take it again and again to be able to get an infinite path. But we will look at finite paths for now. So a path is a finite sequence of vertices, let's say v1, v2 and so on up to vn, such that each pair of successive vertices in the path is connected by an edge. So if I go back here to the example graphs that we saw in the first slide, right? Here is a path in this graph. It begins at u. From u I go to w. From w I go to x. From x I can go back to u. And let's say from u I go to v. Right? So this is a path in the graph. So what is the length of the path? When you talk about the length of the path, we count the number of edges in the path. So the length of the path is the number of edges. A single vertex could be a path, and the length of such a path will be 0. Right? So what is a subpath of a path? A subpath of a path is just a subsequence of vertices that occur in the path. If we go back to that example graph that we had in mind, I told you W, X, U, V is a path, right? In this, there is a subpath, which is say W, X, U, V. That's a subpath. U, W, X is another subpath. So it's just a subsequence in the sequence of vertices that you encounter in the path, right? So why are we looking at paths? We are looking at paths because we are going to be able to design test cases that we can use these paths to reach a particular statement or a particular node in the graph corresponding to that software artifact. So we say a particular vertex B is reachable in the graph if there is a path from one of the initial vertices of the graph to V. For the sake of reachability, we'll consider those paths that begin at initial vertices only, because we want to be able to satisfy the RIPR criteria, if you remember, right? RIPR, the first R is reachability. Reachability means from the inputs or from the initial state of the corresponding graph, I should be able to reach a particular vertex, and moving on, I should be able to propagate the output to a particular vertex, right? Those final vertex to which the output is propagated and visible to the user would be one of the final vertices. So we say a particular vertex V, it's reachable in the graph if there is a path from one of the initial vertices to that vertex V in the graph, right? Reachability is not restricted to just vertices. You could talk about reachability for an edge also. So when is an edge reachable in a graph? We say a particular edge is reachable in a graph if there is a path from one of the initial vertices to the beginning vertex of that edge, which is U, and moving on, it actually uses that edge to reach V, right? So there is a path from one of the initial vertices to the edge, to the vertex U, and then it uses the edge UV to be able to reach the vertex V. Then you say that the edge E, which is given by the pair U, V, is reachable in the graph C. I hope you know the notion of a subgraph of a given graph. So what is a subgraph of a given graph? It has a subset of the set of vertices, and then it has a subset of the set of edges restricted to only those vertices that occur in that graph. So if you go back and look at the same example that we had, so here is a graph. I can think of just this triangular entity, right, which consists of three vertices, U, X, W, and these three edges, as a subgraph of this entire graph. Or you could just consider just the standalone vertex V and another standalone vertex Y as a subgraph just containing two vertices, right? So we can talk about reachability for subgraphs also. So we say a subgraph G prime of a graph G is reachable if any of the vertices in that subgraph is reachable from the initial vertex of G, right? So how are there algorithms that deal with computing paths and computing reachability of a particular vertex? Of course, I'm assuming all of you know basic graph algorithms. In case you don't know, please feel free to look up NPTEL courses that deal with design and analysis of algorithms and get to know about graph algorithms. Two basic algorithms that you have to be familiar with are what are called breadth first search and depth first search. Most of the test case design algorithms that we will deal with in this course will involve depth first search or breadth first search, along with some manipulations and add on to these algorithms. I will not be able to cover these algorithms because I want to be able to focus on test case design using graphs, right? So now, instead of looking at arbitrary paths in graphs, we will see what are test paths in graph, right? So what is a test path? A test path, as I told you, has to begin in an initial vertex to be able to ensure reachability, and it has to end in one of the final vertices. So a test path in a graph is any path that begins in an initial vertex and ends in a final vertex, right? So if I go back to the same example, if I see here, a path of the form UXW is a test path because it begins in an initial vertex U and ends in a final vertex W. Whereas a path of the form UWXY is not a test path because even though it begins in an initial vertex U, the vertex that it ends, which is Y, is not one of the final vertices. So for us, test paths will always begin at initial vertex and end at a final vertex, right? So test paths will result in some test cases being executable, right? Test paths, if some test paths can be executed by test cases, then those are called feasible test paths. There could be test paths for which I can't execute any test case. Like, for example, there could be a test path which says you somehow reach a piece of dead code or unreachable code. So I will not be able to write a test case that you can reach the dead code with, right? So such test paths would be called as infeasible test paths. We will make these terminologies clear as we move on. So a few other terminologies we need to be able to start looking at algorithms for test case design. Those are the notion of visiting and touring. So we say a test path P visits a vertex V if V occurs along the path P, right? Similarly, a test path P visits an edge E if E occurs along the path P, right? A test path P tours a path Q if Q happens to be a subpath of P. So we'll go back to the same graphs that we looked at. So here is a test path, right? U, X, W, right? So this test path visits three vertices, U, X, and W, and it visits two edges, the edge UX and the edge XW, and it tours a subpath WX, right? You could consider another test path which looks like this. It could be U, W, X, U, W, right? So this test path visits three vertices U, X, and W. It happens to visit them again and again, but basically it visits only three vertices, and it tours the subpaths U, W, X. So I hope visiting and touring are clear for you. We will look at what are tests and test paths. Let's take a small example. Look at this graph. This graph has got four vertices, U, V, W, and X, right? And here is an initial vertex U. It models control flow corresponding to a simple switch statement, switch case statement. The switch case statement is at the node U. There are three switch cases. If A is less than B, you go to B, execute maybe some statements. If A is equal to B, then you go to W and do something else. If A is greater than B, then you go to X and then you do something else. And it so happens that computation terminates at X, right? So suppose I have a test case input A as 0 and B as 1, then which is the condition that it satisfies? It satisfies A less than B, right? So which is the test path that this test case executes? This test case executes the path U, V. And remember, test path is one that has to end in a final state, right? V is not one of the final states. Which is the final state in this graph? It happens to be the state X, right? So I go from U to V because my test case satisfies the predicate A less than V. And I can freely go from V to W and then from W to X because these two edges in this graph don't have any guards or conditions labeling them. So if my test case input is A0 and B1, then I say that the test path that it takes is U to V because it satisfies A less than B, and then V to W and W to X. Is this clear? So similarly, if my test input is, let's say, A is 3 and B is 1, then in this switch case statement, the predicate that it satisfies is this A greater than B, and then the test path that it takes is just this single edge UX. It just so happens that this path containing just this one edge already is a test path because it begins at the initial vertex U and ends at the final vertex X, right? So similarly, when I have a set of test cases, I can talk about a set of test paths. For each test case in the set of test cases, you consider the test paths that they execute and take the union of all the test paths to be able to get the set of test paths corresponding to a set of test case. Please remember that one test case can execute many test paths, right? This example doesn't show that, but one test case can execute. Like, for example, if I club these two conditions, right, and say A is less than or equal to B, then I can write several test cases, right, that will execute this path. Now we'll go back and see reachability in the context of test paths. When we define reachability for graphs, we defined it in a purely syntactic nature. We say a particular vertex V is reachable if there is a path from the initial state to one of the vertices, right? As you see in this example, it need not be purely syntactic because there could be conditions associated with edges. There could be something associated with vertices. As you traverse along a path, you are implicitly allowed to traverse only if that condition or guard is met, right? So, in the real application of graphs, we would be looking at reachability in the presence of these additional annotations and conditions, right? So, we will see what reachability means in the presence of these conditions, right? And it is to be noted that if I have a particular test path that is infeasible, like I told you, right, a test path that insists that you reach a piece of dead code, then it corresponds to vertices or nodes or edges or graphs that are not reachable from the main graph. Like, for example, it might so happen that the control flow graph of a particular program has two disjoint components, in which case, suppose I insist that, and all the initial vertices are in one component, I insist that you reach a vertex from the initial vertex to another vertex in the second component. Because these two are two disjoint components, I may not be able to reach that vertex at all, and I say that it represents an infeasible test requirement. So we'll see several examples of where infeasible test requirements could occur when we look at graph models. Right? So how are we going to use graphs for test case design? We will develop a model of a software artifact as a graph. I already showed you two examples of how to take a code snippet and write a control flow graph corresponding to that, right? It is to be noted, as we saw in that example, that these graphs, apart from vertices and edges, could contain several different annotations, labels, right? So here are some examples. Some of the vertices could be initial and final vertices. It could have labels of statements, predicates associated with its vertices and edges, as we saw in those two examples. In addition to that, it could have data values for variables that are defined at a particular statement, data values for variables that are used at a particular statement. Such graphs are called data flow graphs. I haven't shown you an example in this slide, but in later lectures, we will see what data flow graphs look like. But what is to be remembered is that they will typically, graphs that model software artifacts will always have some kind of labels associated with their vertices or edges, right? So we want to be able to use one or more reachability algorithms to be able to design test cases for these kind of graphs. Right? So we'll redefine what test requirement, what test criteria are now specific to graphs. So what is a test requirement? It just describes a property of a test path as it corresponds to in a graph. What is a test criteria? Test criterion is a set of rules that define the test requirement. Like, for example, if you take this graph that we looked at earlier, the test criterion that it describes is to say do branch coverage on the vertex U. Means the degree of vertex is the out degree of the vertex U is 3. There are 3 branches going out of U. Write test cases to cover all 3 branches. That's what we did here. We wrote test cases to cover all 3 branches. So what is satisfaction? We say a particular set of test requirements satisfies a coverage criteria C if the test cases that are right for that test requirement satisfy all the test paths that meet the requirement. Like, for example, if my coverage criteria says branch coverage at node U, then these 3 test cases, right, completely achieve branch coverage for this particular node U, right? So moving on, we will look at 2 kinds of coverage criteria related to graphs. The first coverage criteria that we will be looking at is what is called structural coverage criteria, where we will define coverage criteria purely based on the vertices and edges in the graph, right? They could be annotated with statements and so on, but we won't really use what the statements are or the other annotations to be able to define the coverage criteria. We will purely define in terms of just vertices and edges. The next kind of coverage criteria would be data flow coverage criteria, where we again look at graphs that are annotated with variables and so on, and we will define coverage criteria based on the annotations, based on the variables and the values that they define, right? So in the next module, I will begin with structural coverage criteria and walk you through algorithms and test case design for achieving various kinds of structural coverage criteria in graphs.